Hi, and welcome back to another one of my videos. As you can see from the title, we're going to be talking about crates and ramps today. And I've actually taken the liberty of actually making a problem for you this time. Because I understand with all the previous videos I have not actually set numbers in and we can actually compute things. I just have variables. So for this, I've actually created a problem for us. And it says, a man is pushing a 20 kilogram crate up a ramp horizontally with a force of 200 newtons. So in just analyzing any problem, break it up into pieces, is my opinion. So don't tackle the whole thing. Don't read it all at once and be like, that was nonsense. Don't do that. Just break it up into pieces. You're like, a man is pushing a 20 kilogram crate up a ramp. So just pause, right? M equals 20 kilograms, Same thing for all this, 20 kilograms, 200 newtons, the ramp is set at a 30-degree angle and has a coefficient of friction of kinetic friction of 0.2 with the crate. And so you got mu k equals 0.2 and you have theta equals to 30. And so once you have all those written down, then you can read it a little bit more, figure out what the main idea is. But, read it first just to get everything written down is what I would say, and then read it to visualize it a little bit better, But definitely pick the pieces out to start off. But anyway, so man is pushing a 20 kilogram crate up a ramp horizontally with a force of 200 newtons. The ramp is set at a 30-degree angle and has a coefficient of kinetic friction of 0.2 with the crate. What is the man's acceleration, velocity, and position after 2 seconds? So basically we need to get the acceleration, and then we need to get the velocity and position after we know what the acceleration is. Because the key to this is the acceleration, just because we have to do the sum of the forces to find out what the acceleration is, and then go from there. So in order to do that, we need to create a free body diagram of the scenario, which is what I've done over here already. But just ignore this right now, and we're going to develop this real quick by just looking at this picture, just because you're going to be given a picture like this, and you're going to be like, there's no forces on it. It could be any different forces. I give up. Don't give up. Don't give it up. Just like we did with this problem right here. And we decomposed it to get all the information out, we're going to have to decompose this picture, So basically we have a man right here. And this man is just going to be pushing horizontally, so with a force F, And so I have that right here. And so it's completely horizontal. This guy's not very smart, apparently. But I set the problem so it would just be horizontally, just to show some later things on. But yeah. Anyways, so we have a force right here, and then since it's on a ramp, we also have a normal force, normal to the ramp, so like so, and then we have our weight always, which points directly down. Let me draw that a little bit. So completely vertical. Your weight's always up and down. It's never somewhat to the right or somewhat to the left. It's just vertical. Just always vertical. Even though the ramp's not vertical, so. But anyway, so you have your weight, and then since you have friction on the ramp, you also have a friction force. So that's all the forces that are here. There's no springs, there's no ropes, so there's no tension, there's no spring force. These are all the forces you're going to be needing for this problem. And so if we're going to continue on, we're going to have to tilt our axes for this problem. So if you've watched any of the other videos, you know that your axes are supposed to be like this, X, Y, X is horizontal, Y is vertical. However, for this problem, we're going to want to tilt our axes. So our axes are going to be more or less like this. This is going to be the new X, this is going to be the new Y. So X is completely up the ramp and down the ramp, and Y is off the ramp and into the ramp. And so the reason why we're doing it like this is just because it's going to be so much easier. So since there's going to be acceleration up and down the ramp, and 0 in essentially the y direction now, we're going to want it in to tilt our axes. Because if we kept it like this, then we would have our acceleration basically in this direction, and it would be somewhat in the y and somewhat in the x. But then it's just a little bit less arbitrary, and it's just a lot harder. So just don't do this, do this. So tilt your axes. So, and the reason being also is just because like typically, like if you had a force that was pushing on this box, it'll probably be up, or it'll be from any direction in the end. But in the end, you would only have like the weight that's in this coordinate system. This is the only one that's already in the coordinate system, and you don't have to break up into components. When you tilt your axes like this, then you notice that oh, the normal force is completely in that direction, and oh, the friction force is completely in that direction. And if you had your force being pushed horizontally up the ramp, instead of just horizontally, then that would also be in this coordinate system. So this is just a much nicer way of going about the problem. So you could not tilt your axes, but you're making your life 10 times harder. 10 times harder. I'm telling you. So, and another thing I want to note out before we continue on is that don't draw your ramps like this. Draw them like this. Reason being is your x is going to point down the ramp then. So it's almost like you have positive acceleration going down the ramp instead of having positive acceleration going up. Up should be positive, down should be negative. That's just my opinion on it, so but yeah, so just draw it where your angle is like this on the left side, then your angle being on the right side. So now that I've made our free body diagram and I've gone over my rants, of course, we're gonna have to do the sum of the forces now. So we did our free body diagram, next step sum of the forces, step after that sum of the moments. So just get in the habit of doing that every time if you get stuck. And if it's not an energy problem, so. But anyways, we're going to start off by doing the sum of the forces in the y direction. So we could start off in the x direction, but that has our acceleration in it, and, it's just less, it's harder to solve. So the acceleration goes in this direction, but there's zero acceleration in the y direction, so it makes things a little bit easier. So if we do the sum of the forces in the y direction, we're going to set it equal to 0 immediately, because the box isn't going off the ramp or into the ramp. And then that's going to equal, so we have our n, our normal force, it's completely in the y. And then we have our force that the person's pushing with, and then we have our weight also. And those need to be broken up into components now that we've tilted our axes. So the components of your weight are going to be like this, so it's going to be like that. And then also like that. And then for your force, it's going to be like this. And it's going to be like this. So, and remember, this has to be 90 degrees every time. Your components, when they touch, have to be at a 90-degree angle. Otherwise, they're like fake components, in my opinion. So, but anyway, so now we have to just figure out these triangles and the angles involved. So this angle is pretty easy. This is 30 degrees. It's the theta, just because if it's horizontal to the ramp, then it'll be like this. That's theta. So that was terrible. It would be more like that. This is theta. So a little bit better. But anyways, so we know this is 30 degrees right away. It's theta. So now the real question is this triangle. So now we have to get theta somewhere in this triangle and relate it to these angles somehow. So I have a really easy method of going about this. Probably one of my favorite methods. It's so easy. So if you have your weight going down like that, and you want to make it into components like this and like this, so a component going perpendicular to the ramp and a component going parallel to the ramp. So in the end, if we just translate this down to here, just move that triangle, it's going to be like that, and it's going to be like that, and then it's going to be like that. And so since this vector is normal to the ramp, It's going to be perpendicular like that. And since your weight is completely vertical, meaning it's perpendicular to the horizontal or x, this direction. I guess it's not x because this is x now, but the horizontal. So this is also 90 degrees. So let me draw that a little bit better. So that's 90 degrees then. And so really what I want you to do in the end is just take a piece of paper. It's as simple as that. Take a piece of paper and put the edge right here. And since you're finding out what this angle is, because that's a question mark, it's a mystery, well, take that piece of paper, hold it right here, and then just twist it so it would be on top of it. So basically you're twisting this piece of paper this many degrees. And so once you twist it that many degrees, you'll know that the top of the paper now is right here. You know, that the top of the paper moved theta. So if you twisted the piece of paper this many degrees, you moved it theta. So that's just probably one of my favorite proofs that I have, just because it involves nothing. Nothing. If you can rotate a piece of paper, you can do physics. You know, there should be no question about that one, at least in my opinion. So this is theta. So whenever you get stuck, put this right here, rotate your piece of paper, and you'll find out that this is theta, not this. So anyways, this is going to be theta then. And so now that we have all our angles, we're ready to continue on. So now we need the y component of the weight. So that's going to be minus, since it's in the negative y direction, mg. And then it's going to be cosine of theta, because it's the adjacent side. So cosine theta. And then we also have to include the y component of the force, F. So, and that's just going to be, the sine of theta for that one. So it's going to be minus F sine of theta, because it's the opposite side. So now that we have this all set up, we can essentially solve for what n is, and it's going to equal basically mg cosine theta. Write that a little bit better. Cosine theta. And then we're going to have plus f sine of theta then. So now let's do the sum of the forces in the x direction. So if we do that, then we have the sum of forces in the x direction, and that's just going to equal mass times acceleration, just because we're headed up the ramp, you know. Technically, we could be headed down the ramp if he's not pushing hard enough, but you know, I set it up where he's pushing hard enough. So, so anyways, then that's going to equal, so now we have all our x components to worry about. So we have f cosine theta, that's in the positive direction. And then we have our x component of our weight, which is going to be in the negative direction, which is going to be mg. And then it's going to be sine of theta, because it's the opposite side. And then we're going to have our friction force involved, which is just mu k times by n. And then we found out what n was earlier. So now what we're going to do is we're just going to actually plug this into here. So then we get mass times acceleration equals f cosine theta minus mg sine theta minus mu k, parentheses, plug this all in now, so it's just going to be mg cosine theta plus f sine of theta. So now we can start like plugging in some stuff. So just, you know, we got to make it a little bit easier for ourselves. But so cosine of theta is just going to be the square root of 3 over 2. So we can just use our unit circle sheet, or, you know, I guess our heads for this one. So, and then sine of 30 degrees is going to be a half. Cosine 30 degrees is square root of 3 over 2 again. This guy's a half again. So So now you can start plugging in numbers. So we're going to have basically, so it's going to be 200. Turn it on. So 200 times by the square root of 3 over 2. So really that 2 is going to cancel with this 2, make it 100. So it's going to be 100 times by the square root of 3. And then it's going to be minus. So, and then we have 20 for our mass times by 9.81. And then divided by 2, because it's a half. And then we're going to have to minus, and then mu k is 0.2. So 0.2 parentheses. So then it's just mg, which is 20 times by 9.81 times by the square root of 3 divided by 2 plus, and then f times by half gives you 100, you know, as we saw right here, you know. Close parentheses. Should be good then. So we get 21.1 in the end. And since our mass is 20, we just divide that by 20 then. So then our acceleration then is going to equal, so divide that by 20. So our acceleration then is going to equal 1.06 then. And that is going to be in meters per second squared. So that's our first answer. So as you can see, this is just a number in the end, you know. It's just like a equals like 2, you know. It's just a constant in the end. It's just, which seems really peculiar, you know, just because like we did all this work up here and we're like, oh, A's 4, you know, A is just something, you know, it's not, we like normally you'd probably expect like a function to be right here, but it makes sense when you start looking at all the parameters individually, you know. So like if we look at f is equal to 200. F is not equal to 200t, you know, is not a function in the end, and neither are all the other parameters. And so if we have all constants being multiplied and subtracted and whatnot on this side, and we're dividing by a constant in the end, which is the mass, then we're going to get a constant, you know. So it makes sense that the acceleration is 1.06, you know. It just seems a little awkward, you know. It's just, you know, like why would this guy be pushing and having it go at a constant acceleration? It seems a little off, you know. But you know, it helps us out in the end, you know, just because having a constant acceleration means it's really easy to get our velocity and position for the problem in the end. So. And basically, when I say a constant acceleration, something should pop out immediately. You know, like especially if you watch the previous videos that I've had. Basically, in the end, when I say constant acceleration, in the end, you should really think kinematic equations. You should always think that constant acceleration, kinematic equations. You know, they're linked basically. You know, just link them in your brain. But anyway, so we're just going to use those just to develop our velocity and position in the end. And so I'm going to start off by using the most famous kinematic equation, which is just going to be like s of t, or delta s, equal to basically a half a t squared plus v naught times by t. And then it would be like plus s naught if this was s of t. But since I have delta s over here, it's like if we subtract s naught to this side, and then we have delta s over here. So I'm just going to get rid of that, and so really delta s is just going to be like that far up the ramp, you know. But anyway, so another thing I didn't note when doing this problem is that the velocity is 0 initially, you know. The man is going to be starting from rest, and typically that's the case, you know, and it would say like the man starting from rest in the problem. So this is just going to be 0 in the end, and then so delta s then is just going to equal a half times by a t squared. Our time is just 2 seconds in the end, so it's just t equals to 2. And then so really this is just going to be a 4, and then if we divide it by 2, we get 2. So it's going to be 2 times the acceleration gives us delta s. So if we bust out our calculator then, times that by 2, what do we get? 2.11. And that's going to be meters in the end. So that's our position in the end. So now we need to get our velocity at 2 seconds. So that's just going to be, we're just going to use the derivative of this equation then, you know, which is just like v of t equals a times by t plus v naught, you know, but v naught's the 0. So so in order to calculate v of t, it's just going to be 2 times by our acceleration, which is exactly what we did for the position. You know, like if you look at the calculator, acceleration times by 2, you know, which is kind of weird, but you know, it's just because it's a half right here. 2 squared is 4, you know, it just worked out that way. If this was like 3 seconds, then they would be different, you know. It's just a coincidence in the end. So in the end, v final is then going to equal 2.11. Instead of meters, it's going to be meters per second. And that's it then, you know. I guess I'll go back over it real quick, I guess, before I end the video. So basically all that we did is we just, you know, got our parameters from the equation, you know, just wrote them out right here, you know, read the equation a little bit better. And then after that, we did the sum of the forces in the y, just because, you know, that should equal 0. So we would want to start off with that one. And then we did the sum of the forces in the x. And then we plugged in the normal force that we found for the y direction. And we plugged it into this one right here, and then found out the acceleration. And then we used the kinematic equations, like so, and we got the position and velocity. So, and that's it. So, see you in the next video.